In this video, we're going to look at testing a claim about two means when we're dealing with independent samples. Now, if we're going to talk about dealing with independent samples, we should first define and figure out what it means to have independent samples. So, two samples are independent if the sample values from one population are not related somehow or naturally paired with samples from the other population. So if they are not related somehow or naturally paired. So this should be a natural pairing that we're looking at and trying to see if we have, if there's not, even if we can pair them up, even if we have the same number of items, if there's no particular reason why a value in the first population goes with a value in the second population, we would consider these independent. They are said to be dependent or matched pairs if they are related, if they are naturally go together. Right? So things that are matched pairs would be things where you have like a before and after. Right? So a amount of pain before you take a medicine and the amount of pain after the medicine. Or if you have a couple and you are looking at how the first person in the couple, how many hours they spend watching Netflix as compared to the second person in the couple. There's a natural pairing there. Maybe there's not a reason why one person would watch more Netflix if their significant other watched more Netflix. But maybe there is a relationship. Maybe they're more likely to watch Netflix together. And so those would be dependent or matched pairs. And so when we have a natural pairing, or they're related somehow. If it's not a natural pairing, even if we can pair it, then it would not be considered a dependent sample. Instead, it would be independent. When we're dealing with these means, and we're dealing with a hypothesis test here, our null hypothesis is that the two means are equal. mu1 is equal to mu2. And just as we've talked about before, we have three different possible alternative hypotheses. So one of those is they're just not the same. I don't know if mu1 is bigger or mu2. I don't really care. I just care that they're not equal as an alternative. And then we could say we care how they're not equal. We care because we want to see is it actually the case that mu1 is bigger than mu2? Or is it actually the case that mu1 is less than mu2? So we might have these one-tailed tests where we are stating which mean we believe to be bigger as the alternative. Similar to the way we interpreted confidence intervals for proportions, for means we have the same thing. Our confidence interval is going to look like a number is less than mean 1 minus mean 2 is less than some other number. And so when we have 0 in the confidence interval, we are saying that it is reasonable to believe that mu1 minus mu2, it's reasonable to believe that that is equal to 0. Which would imply if you added mu2 to both sides, it's reasonable to believe that mu1 is equal to mu2. Now, when we say that 0 is in that interval, really what we're saying is a little bit more than that typically. We're usually saying there are values that are negative in this confidence interval and values that are positive. And so it could be negative, it could be positive. If it was positive, then mu1 would be the bigger value. If it was negative, then mu2 is the bigger value. And if it's 0, then they're the same. And so that's why we don't ever say there is evidence of the null hypothesis. We will just fail to reject the null hypothesis. We can't say it's not true. We don't have evidence of the alternative explicitly. This is still reasonable to believe. However, so when we have 0 in that interval, it's reasonable to believe the two means are equal. If it is strictly greater than 1 or greater than 0, if it only contains positive values, then we have evidence the first mean is greater, or we have evidence that they're not equal. We have specifically they're not equal in the way that the first mean is greater. And if it's only values less than 0, then we have evidence that the first one is smaller. We have, again, evidence that they're not equal, specifically the first is smaller. When we go through hypothesis tests here, we're going to have 3 different cases when we're dealing with 2 independent means. Each of these cases will be really subtly different. So the first is the population standard deviations, sigma 1 and sigma 2. Those are unknown, and not only do we not know them, we also don't believe them. We don't assume them to be equal. Maybe they are. We just don't make that assumption at the beginning. It's possible that we know the values of sigma 1 and sigma 2, so that's case 2. And then case 3 is we don't know them, but we are going to assume that they are equal. And so those will be the 3 different cases. We will talk about those in the next few videos. We'll deal with each case separately and look at associated examples. We will talk to you there.